Hi and welcome to the tutorial about how to make a four-leg IK in Unreal 4 using a Control Rig plugin and full body IK. So we will be using this wolf here, and the final result will be something like so. So as you can see, we can see the leg IK very well. This wolf, it was a free asset of the mount once on the marketplace, so we took it, and it came without any blueprint. So we made this anim blueprint and put it on our ArtStation store that you can check here. There is both paid and free version, and the wolf itself can be found here on the marketplace. I'll put the link in the description. So this wolf, it can walk, as you can see, run, jump. It's a pretty complete character. Swim. And it also comes already with an IK. But here we will recreate this IK with Control Rig plugin and full body IK. So that's the result we will achieve. This tutorial is a third part of our Control Rig tutorials. In the previous two parts, we explained how to create a control rig, how to hook control rig with anim blueprint, and how to make a two-leg IK using control rig and two bones IK or full body IK. In this tutorial, we will see how to make four legs IK using full body IK. So if you didn't see the previous parts, I suggest you see them first, but because here I will not explain everything from scratch, but I will just show the parts are different. So let's see about this wolf. First of all, the skeleton. So this wolf, it has pretty small skeleton. Here I have those virtual bones we will not be using. Those are used for our other IK implementation. But with the control rig, as we will see, you don't really need the IK bones or virtual IK bones. You can do everything in one step, so those are not used here. So we have basically root. There's a bone called CG, which is like another root. Then you have normal skeleton, you have pelvis, then to pelvis is connected the spine. Two spines are connected the rear legs, and then the front legs are connected to the neck. Front legs are, as you can see here, composed of clavicle, upper arm, forearm, and hand, like human arms. We will be driving all four of this. We will be using all, of course, it's a full body IK, so we will be using the whole arm, including the clavicle. And the back legs, here you have the typical dog leg with this bone called horse link. So you have, usually you have thigh, knee and foot. Here you have thigh, calf, horse link and foot. And usually with this kind of setup there is a problem that it's not straightforward to use 2 bones IK, because simply there's 4 bones. And a good thing about full body IK is that you can use it with this setup with any special, you know, with no additional complexity. You just need to set up some constraints properly. So that's what the wolf. Now let's check the rig. So here it's basically like the rig for the human. So we have different parts here. As you remember from the previous part of the tutorial, first we need to store the location of the effectors in the temporary bones, because at some moment in the calculation we will move the pelvis, so every effector bone, every end bone will move with it, and we need the position before we're doing that. So here, first thing, like for human, we will save the we created here various temporary bones, which are user space bones. So it's, I mean, I believe they're created, they're called user bones, yeah. So you just click here and you say add bone, and those bones exist only in the control rig. They don't exist in the skeleton. And what we need is to first save the location of the foot, hand, neck and head into toes. And we use the node called set relative transform, which copy the transform of one bone to another. And we could put you know, like six of those, but instead we use a feature called collections, and for each node. So those collections actually are divided here, and a collection is just an array containing bones, or it also contains controls or other type of, you know, those things that go to the rig hierarchy. So here we have those bones, neck, head, foot and hand, and we save them to a variable, which we define it here, call it to copy. And we also have another collection that we save a variable, call it to rotate. And here we just take this variable and we iterate over the content of this array. And what we do, we take the name of the bone, which, for example, neck, and we prepend the tempe to it, and then we copy the transform of the neck to the bone called tempe neck, which is our temporary bone here. And so it will be the same for every one of those 6. And so we just use it, you know, the fact that we call it the bone the same, like neck, and prepend the tempe to it. So it works here. And as you see, we create those collection in a special part of the graph, which is called setup event, that you obtain simply like so. And this is different from our usual entry point, which is forward solve. It's the like on initialize. It's the entry point called once when the rig, when the animation is initialized. So at the very beginning, we will on init we will create those collections, so we don't have to recreate them every time. It's mostly to show you this event. You can also set up some bones here, etc. And so we made a copy of everything into temporary bone. The second part is exactly like for human. We took every foot, one of every of 4 feet, paws, and we make a trace. And the goal of making this trace is to find the difference between the location of the flat foot, which is on the same level that the root bone, and the real, flat floor, sorry, and the real floor that you have this in the level. So you see on these spheres the floor is obviously not flat, so we will search this offset. And as I said before, you can watch the previous part, it's all explained, it's various pictures and stuff like so. So we will take our hand and feet bones and make a trace from above to below and store the result of the trace in a variable here and here. And we will also aim the temporary effector bone so it follows the heat normal, the normal of the floor. And so we have to make that 4 times instead of 2. And what I put here, I made a little debugger. So instead of when you are here in the preview, you don't have the floor here. So instead of relying on those traces, we can just put some controls and move them. And here we will initialize those variables simply by taking the relative offset of the control. So if I enable this part, I can already debug my algorithm like so. Okay, now next, once we made the toes, we can start to apply the algorithm. And as you remember, you first have to move the pelvis bone to the lowest foot. In this case, it will be rear paws that are interest us. So we will move the pelvis to the lowest floor on which the rear legs are standing. And doing this, we will move, of course, the whole body, because the whole body is attached to the pelvis. And next thing, we will do the full body IK. It's exactly the same like for the human, only that we have more legs. So here we will start by inputting the effectors in the full body IK node, and we will put the pelvis, which was already modified here, location, rotation, and then we will add the feet, 4 of them. And as for with the human, we will take the temporary foot, and the effector will be the position of the foot plus the offset. So we will move the foot higher or lower relatively to its initial location. And then different part here is that now we have those 4 paws. So for the rear legs, it's exactly the same. We move the rear legs, and we move the pelvis to the lowest of them. But for the front leg, they are attached to another bone. They are attached to the neck, actually. Here you can see it. They're attached to the neck. You have neck, then you have clavicle, upper arm, forearm, and hand. And so we need to, where it is, neck here. So we need to remake the same kind of calculation for the neck. So basically what you have is that you have two leg IK for the back and for the front, and here you have this neck bone to which the legs are attached, and you offset it by the minimum of the two front floors. So you check the two front floor offset, you take the minimum, and you add this offset, which can be positive or negative, to the to the neck bone. And if it's positive, well, if this leg is higher, right leg is higher than the left leg, though, the minimum will be 0, so neck will not move. And if this leg is lower, the neck will be also pulled down. And I also entered the head here because I kind of like more how it looks like. And you also have to add this offset to the head, because otherwise the head will stay, probably too high. So you need to add the same offset that you add to the neck, to the head, and input it as the effector. So that's it. And as you remember with the with the human, the full body IK, as we set up it, we remove the force effect rotation target, because the result this thing produces, they are not very good for the mid effectors, so for the neck and for the pelvis. And instead we just manually force the end effectors, the pulse and the head. And for this we again use a for each loop, using those to rotate nodes, bones, collection of bones we defined it in the very beginning, which are the feet and the head. So those are our end effectors. And what we do is to taking the rotation of the temporary end effector, which was calculated here according to the normal of the floor. That also was explained in the previous part. And then we set the rotation of the bone to that. And that's it. As you can see, oh no, sorry, not that's it. There is another important part. We've seen how we input the effectors, but there's only another important part with the full body IK. Like I said in the beginning, we have this 4-bone leg here, dog leg. So another important part is to look at those constraints. And of course there's more constraints than for the human. So let's briefly look at them. First of all, we have the constraints for for the front legs, call it arms here, and so those are working like that. They bend mostly on the z-axis. So z-axis is the this one, and same here and same here, and the axis that follows the chain is the x. Right. See it. Oh, this is clavicle, sorry. Where is the x? And for the legs, for the rear legs, they also bend on the z, and the axis going down is also the x. So what we want to do is to avoid those legs bending like so, because that's not possible. We need them to bend like so, and probably some of them, like the feet, a little bit like on the x. And we specify that with those constraints. We say that the forearm bone angular stiffness, it 1 on the y-axis, meaning that it cannot bend on y-axis. It's very stiff. 0 stiffness on the z-axis. That means that it's okay to bend on the z-axis. That's the axis we want really to use for bending. And here I put a little a little bit of stiffness on the x, but not full stiff, just half. So I can a little bit rotate like so. That was the forearm actually, like so, but not much. So it's the same for the other forearm. Clavicle is just a little bit stiff on the both axes but z, and basically you play with those. And then for the spine, yeah, I put those numbers, but you can also play with those and see what works better for you. For the spine, it works like so. The forward axis is x, and the y-axis is this axis bending like so. And I don't really want it to bend like so too much. And the z is this. So what I use it here on the spine, is to put z to a little number, and y to almost stiff, so it almost not rotating like so, and x is 0.5, so it's like I don't really want to rotate this way. It's okay to rotate this way, but it's a little bit more stiff on the legs, so it will rotate a little bit less. Legs will be preferred, and it can rotate a little bit like so, because like if I pull one leg up, it can do some kind of movement like that, but not too much. So that's for the spine. And I also have the constraint for the neck, like for the rest of the spine. It's a little bit stiff and it should not bend too much. yeah, that's it for the constraint. And for the rest of the setup, I here again lowered both damping and iterations. That it's just for the you know, reasons of performance, because by default it's 30-30 and it worked very well, but here it doesn't work because I keep the bug. It worked very well, but it's a little bit too slow. And so we'll put it to, for example, 6 and 6. And here I also lowered this value because I find it's reaches the end position for the foot a little bit better. By default it's 2. But I'm not very sure about this one. Maybe better to leave it at 2. And yeah, so this is done. And now we can, as before, just try to check the performance of this thing. So I will record some here, and look what we have now. We are looking at the onion blueprint, which is, where it is, this one, on the end where we were standing. And yeah, as you can see, it's not exactly what you would call fast. It takes almost 1 and sometimes even a little bit worse milliseconds. So that's the main problem of this algorithm right now. And as I said in previous videos, I think probably it will be improved, because now it's still in very early stages, and I think even when looking at the code, there are things they said will be improved in the future. So let's hope. But as you can see here, the algorithm itself, it has a lot of very powerful features, like, you know, it's like just one node, you put all your effectors, and it does pretty good job, very good job at putting your character in the right pose. It also automatically solves all those problems with you know, four-bone legs, and it also solves, in my experience, a lot of problems with the, you know, bones overextending or over compressing, because it will, you know, it will take into account the whole body. So for example, if you try to pull one bone too far, it will also pull the parent and the siblings. So with the other algorithm that I implemented, that you find on this onion blueprint on the marketplace, I made basically two two legs IK, so like for two people, and then a spline IK for the spine, connecting the two. And it was really difficult to configure all this stuff together, to work together. And with the FBIK, full body IK, you just took everything you need to control, you put it in here, and you just leave the work to the computer to solve the problem. And that's very awesome. So that's it for this tutorial. I hope it was clear enough to understand. If you have some questions, please let me know. And yeah, that's it. Thank you. Bye.